Swinburne podcasts.
The accelerating universe, discovered through the study of distant supernovae, is one of the greatest scientific discoveries of recent times. It suggests that there is a dark energy which works in the opposite sense to gravity. At the Centre for Astrophysics and Supercomputing at Swinburne University in Melbourne, Australia, a team of researchers is about to embark on a landmark study. The WiggleZ project, which looks at the clustering of matter on different scales in the universe, will provide the first high-precision measurement of this dark energy, independent of supernova observations.
Well, it's a very interesting history to this here because way back in Einstein's time, he suggested the idea of a cosmological constant, which effectively is saying that there is this extra component in the universe, what we call sort of dark energy. And of course, since that time, people never really believed that it existed. But with these new distant supernova results, we now have to take this a lot more seriously. And so we're now in a situation where there seems to be very, very good evidence for dark energy. And of course, the question is, what is that dark energy? One possibility for dark energy is it's an additional force in the universe that's actually operating on the smaller scales as well as the very larger scales. This is something that we call quintessence, an additional fifth force, you might say. So there are two astronomers here at Swinburne University, Professor Carl Glazebrook and Dr. Chris Blake, who developed the idea of how we might use the standard ruler idea to actually measure dark energy.
This goes back to a talk I heard from a guy called Dan Eisenstein, who showed a little picture of what you could observe of a million galaxies. He showed that you could observe these ripples in the structure of matter in the universe, these acoustic oscillations or cosmic sound. And I had the idea that we could use this as a probe of dark energy, because looking at this plot, I thought that we can measure this with a high degree of precision. And so then we went away and did some simulations. This was me and Chris Blake, to see how accurately we really could measure these acoustic oscillations, and found we could measure them to sufficient precision that this would be a very useful measure or probe of dark energy.
So the early universe was a very different place to today, but it's actually a time that we understand very well. We can detect the cosmic microwave background radiation as a dim glow over the sky, and this was emitted about 400,000 years after the Big Bang. Now, the universe was a very different place then. It was so hot that ordinary atoms split up into their separate electrons and nuclei, which existed in a kind of soup or plasma, as astronomers say. Now, the interesting thing is sound waves actually rippled through this plasma. Sound waves of all different frequencies and tones. Now, 400,000 years after the Big Bang, a very special thing happened in the universe. The universe had cooled sufficiently so that these separate electrons and nuclei could merge into atoms, and at that point, the sound waves ceased to travel. This selected a very special wavelength, a scale, a frequency of sound waves, in the same way that an organ pipe will select a given musical note. Now, if we fast forward 14 billion years to today's universe, we can actually detect that faint ripple, that special scale in today's galaxy distribution.
This phenomenon, popularly known as cosmic sound or cosmic ripples or cosmic wiggles, the posh name is barotic acoustic oscillations, which means the same thing, talking about sound waves, acoustic oscillations left over from the Big Bang.
At the moment, there's one main line of evidence for dark energy, which is distant supernovae. But there are a lot of worries in interpreting different supernovae. There might be dust extinction, which dims their light, or their properties might change as they go further away in the universe.
We have no good physical model for how supernovas explode. Whereas with the wiggles, we have these cosmic wiggles, we actually have a very good physical model. Let's just calculate the exact scale of these features, and we can simulate that very precisely. And so it's very independent of the supernovae.
Now, the difference is that supernovae are objects of known luminosity. So when you find one in the sky, you can use its apparent brightness to infer how far away that supernovae is. The baryon oscillations mean that galaxies have a very special known separation. and the apparent size of that separation on the sky tells us how far away that pair of galaxies is. And measuring the distance to different distant galaxies is a very important way of figuring out the properties of dark energy in the universe.
Over the next 3 years, the team will use 220 nights on the Anglo-Australian telescope and 1,400 orbits of the Galaxy satellite. They will observe over 400,000 galaxies. This research is supported by the Strategic Initiative Program Fund for Tier 1 centres and a substantial ARC grant, and investigates one of the highest profile areas of current astronomical research.
Our goal is to actually measure the effect of dark energy to a very precise amount, that is within a few percent. And that's a way of actually quantifying the actual effects of dark energy on the universe as a whole. And so it would be a real triumph for this project if we could do that.
swinburne.edu.au/podcast. Swinburne Podcasts.